make this a little more official. I should have put this on the copies I gave you, but 6-7, again, 6-7 is extra credit. All right, so here's the plan. If you were not here yesterday, I'm going to do a remarkably quick summary of what we talked about, so you should probably watch the video from yesterday. I think I stressed enough yesterday about the pressure I feel as a teacher is interesting sometimes. Trig is crazy important, right? So I desperately am always trying to figure out the absolute best way to get you guys to understand what's most important. So I'm teaching it a little bit out of order from the book. I jumped into 7.2. I haven't talked about 7.1 yet. So if you're trying 7.1 homework at some point, we're going to talk about it today, towards the end of class. I'd like to start with the whole idea of triangles, and I focus on introducing the trig functions, and then I come back and talk about different ways to measure angles. Because the 360-degree thing in a circle is a completely made-up bullshit thing we did. We just were like, I like the number 360. That's literally what we did. Yes? Yeah, I love you guys. How's everybody doing? Okay. So very quickly, can somebody remind me one thing we talked about yesterday? Because I'm an old man, I can't remember.
Cosine, tangent.
Oh, do it again.
Cosine, tangent, cosecant.
Yes! I like it. And how many trig functions do we end up creating?
6.
6. And those are the there are other ones, but they're kind of silly. So those are the 6. And why were there 6? Does anyone remember why it makes sense there were 6?
Is the different ratios of the triangle.
That's as many ratios as you can make between the sides of a given right triangle. You can make 6 ratios. 3 of them are kind of silly because they're just the other ones flipped. So to be really honest, there's 3 primary trig functions. And then the other ones are just flip those. Yes? So it's not surprising we call the 3 other ones reciprocal functions. So let's remember what the hell's going on. So if I have a triangle, bless you. What is sine theta? No. So the way sine likes y. The way I think about sine, this isn't exactly right, but it's fine. Sine is sort of like the percentage of the hypotenuse that's in the y direction. I need you to see this. If I went this far over and this far up, couldn't I have done the same thing by going straight along h? Are you with me? So the percentage of the actual motion that's in the y direction is sort of like what sine theta does. So sine theta, sine likes y. Sine goes like y. As long as my angle is where? In the base. Kick ass. So if my angle is not in the base, I literally just rotate my head or rotate the paper. Okay. What's cosine theta? X over h, because cosine likes x. Cosine goes like x. And what's tangent theta?
Y over x.
Y over x. Now, real quick. I didn't point this out yesterday. But can anyone see what tangent theta is in terms of the other 2 trig functions I've written down?
It's one that
Can you guys
doesn't
do this for me? Can you guys investigate sine theta divided by cosine theta? What is sine theta?
Y over
Y over h. And what's cosine theta?
x over h.
Does anyone know how to simplify that?
remove the h.
Do it again. Yes. The top has a divided by h, the bottom has a divided by h, so they both cancel. Or you multiply by the reciprocal at the bottom and the h's cancel. So what is sine theta over cosine theta? It's y over x, and what is y over x?
Tangent.
Tangent. So what is tangent theta? Another way to say it? Sine theta over cosine theta. So tangent theta, another way to say tangent theta is sine theta over cosine theta. This is why when I teach you, because you're going to have to memorize sine of 30 degrees, cosine of 45 degrees, tangent of 60 degrees. And I try to get you to realize, if you just remember sine and cosine, you can build tangent. So you have less shit to memorize, less stuff to stuff in your brain. If you want to memorize everything, it's always an option. Are you guys at all with me? If I knew what sine of 30 degrees was, and I knew what cosine of 30 degrees was, could I figure out tangent of 30 degrees? Yes, because tangent of 30 degrees would be sine of 30 degrees divided by cosine of 30 degrees. I could build it. I don't have to memorize it. I could build it. Do you guys see what I'm saying? And that's the way I did it as a student. I didn't memorize it. Now I've taught this so much, it's finally in my head. Not because I tried to, but because I did it so many times. I remember it now. And I do have kind of a way to remember it if you want to. So we'll get there. So let me stop for a minute. Is everybody kind of with me? Yes?
What exactly are the sine, cosine, and tangents? Are they the angle or the area? Or
Do it again, sorry.
what exactly are they?
So given, all right, let me ask you this. Let's say I have a rod of length h. Okay, I'm going to do something interesting that I don't normally do, and it's just laying flat. Yes? How much of that is in the x direction? All of it. So what percentage of it is in the x direction? 100%. 1, yes? Is everybody with me? You with me? If I rise that just a little bit, if I rise it to here, it's the same h, yes? But I just kind of picked it and kind of angled it, made a ramp out of it. Do you agree there's now a y component to this? And there's this x component. Is the x component bigger or smaller? In fact, let me do it over here. I got something new today. I got like different colors of stuff. So if I do what I'm trying to do over there, over here, there's now a y component, and this x component, is there bigger or smaller than the original? Smaller. Let me stop for a minute. I need you guys with me. So if I have it like this, it's all x. None of it's y. If I move it just a little bit, if I make an angle here, that's not 0. If I make an angle something bigger than 0, now some of it's in the y direction, and some of it's in the x direction. Yes? So what sine is basically measuring is the relative amount in this direction versus what the whole thing was. Y over h. That's why I said it's sort of like a percentage of the hypotenuse that is in the y direction. So of course here, how much of it's in the y direction? None of it. So what is sine of 0 degrees? If sine measures the amount that's in the y direction, and at 0 degrees, I have nothing, what's sine of 0? 0. What's cosine of 0 if cosine measures the percentage that's in the x direction? All of it. So 1. Is that cool? You guys with me? 100% is 1 as a decimal, yes? The whole thing is in that direction. So the minute I move it, I rotate it, isn't there less in the x direction now? You can think of it as a shadow, the shadow on the desk. So cosine is the length of the shadow straight down. Sine is the length of the shadow like on the wall. Yes? So as I move it, what's happening to sine, the y piece? Is the y piece relative to my elbow here, right? This is the x-axis, yes? So at first, there's no y piece. What's happening to the y piece?
Getting bigger.
Getting bigger and bigger until it's all y. So what's the sine of 90 degrees? If sine measures the percentage that's in the y direction, what's the sine of 90 degrees?
1.
1. How much of it is in the y direction now at 90? Is everybody cool with this being 90 degrees? Yes? This is 90. How much of it is in the y direction? Use words. How much of my arm is in the y direction now? All of it. Yes? So 100%, 1. So sine of 90 is 1. What's cosine of 90? Cosine likes x. Is there any shadow If I have a light straight of red, any shadow? No, so what's cosine of 90? 0. Do you guys, all right, listen, I totally understand. We're just learning this. But accept what I just said. That's really literally all this does. I have an H. The way I orient it tells me how much of it is in the y direction, how much of it is in the x direction. So I have a function, trig functions, that tell me for any given angle how much of it is in the y direction, how much of it is in the x direction. That's kick-ass. That's why we were able to yesterday tell how tall a tree was by just walking away from it and then measuring the angle. Of course I can tell how tall it is, because if I know the angle, I know what percentage is in the y direction. Okay, maybe. Is that better? No? Yes? Okay. You don't have to shake your head yes just to make me feel better. Okay. It's weird. Don't get me wrong. It's weird. Just accept what I've said so far at the moment. You know there's going to be more. But if you realize sine tracks how much y there is. Of course it's 0 at 0 degrees. Now it's more than 0. And now it's the most it could be. Yes? Later we'll talk about what if I go past 90. Things get weird. Give me stuff for that. Okay. So you missed a little something if you missed yesterday in terms of where these came from. But does everyone agree with me if I'm given a right triangle, I can definitely make these ratios between sides? Now the other three, like I said earlier, are a little silly. What's the one related to sine? Cosecant, good. It's literally just sine flipped over. What's the one related to cosine? Secant. And what's the one related to tangent? This is the one that actually makes sense. Cot. So those are the ones in red are reciprocal functions. So when you have to memorize values, like you have to memorize what sine of 30 degrees is, how would you get cosecant of 30? You would just flip what you got for sine of 30, yes? So you don't have 6 things to memorize. You really only have 2. If you know sine and cosine, you can figure out everything else. Do you guys see that? Okay, I like it.
I think the hard part for me would just be remembering that sine becomes cosecant.
What
I
I
know that
did,
you flip it, but
what I did as a student is S goes to C, C goes to S.
okay.
I don't know if that helps. S goes to C, C goes to S. You see that? Right now, it doesn't make sense why tangent and cotangent are the only ones that seem to agree, right? Later you'll see, it's definitely in calculus. There's an interesting thing about all the co-functions that happens in calculus. But later this semester we'll actually see some reasoning as to why we've done what we've done. What have we done? Yes? Yes?
Oh, I remember being taught about instead of y and x, it was like adjacent, opposite. Is that?
I might talk a little bit about that.
Okay.
And I need to soften what I said yesterday. I still stand by what I said yesterday, which is basically I said SOHCAHTOA sucks. But if you've learned SOHCAHTOA, there is nothing wrong with it, except from a teacher's perspective, it gets you this far. And I'm trying to teach you something that will get you forever. I need you to understand what I'm saying. If you know that sine goes like y, cosine goes like x, there's so many other things that just come from that. If you learn SOHCAHTOA, that helps you with very specific problems, and then it does nothing for you on these other things. So if you know SOHCAHTOA, you're fine. It works. But if you incorporate the way I'm trying to show you, you actually have that, those ideas carry longer. Okay. So I got to be softer because a lot of students have learned SOHCAHTOA. You like it. I don't blame you. There's all these silly jokes about Camp SOHCAHTOA and so forth. but I personally, it does not help in the long run. And I'm always trying to keep a mind on what's going to help you in the long run. Because most of you guys want to take calculus. And if you learn sine likes y, cosine likes x, so many things make so much more sense. Anybody going to ever take any physics? Yes? Holy shit. The more you understand sine likes y, cosine likes x, things make so much more sense. Okay, great. So continue using SOHCAHTOA. There's nothing wrong with it, but try to wrap your brain around what I'm trying to say. See how it overlaps. Okay. Well, I might as well pay a little lip service to it right now. What is the side that is across from this angle? What side is across from this angle? Yes. So sine is the opposite side over the hypotenuse. That's SOH. Sine is opposite hypotenuse. That's so from SOHCAHTOA. What's the side that's not the hypotenuse that's adjacent to this angle? X. So cosine is adjacent divided by hypotenuse. You guys follow? SOHCAHTOA works better than my method in only one kind of problem if this is flipped. My method works if the angle is in the base. So all you have to do is flip the dumb picture and you're fine. SOHCAHTOA, you don't have to flip the picture. That's not much of a shortcut to me. You saved yourself 0.7 milliseconds. Right? Okay. So if you do know SOHCAHTOA, it works. I'm not telling you it doesn't work. It's just not useful in the long term. Did this help at all? Because this is huge. If you've learned unit circle, we're going to get to the unit circle, but I'm still going to build it off of triangles, believe it or not, even though it's a big old circle staring at us. There are triangles that live inside of it. So the more you understand this idea, the more this unit circle is going to make immediate sense. As I move up, well, from your perspective, it gets like this. My y piece gets bigger, my x piece gets smaller until I get to here.
When you're using not the SOHCAHTOA method, but your method, or rather, it's not your method, but how do you know when to flip it?
Whenever the angle's not in the base.
Okay, so the base, you want to keep it at x.
So for example, let's do a concrete example. Do you guys like that?
Yeah.
All right. What if I gave you this triangle here? It's not to scale. Let me see. Let me make this a little better. There we go. Yes? That's a nice right triangle. It's one of the ones that has nice whole number sides. Right? There's a 3, 4, 5 triangle, 5, 12, 13, 7, 24, 21. In general, they're going to have radical side lengths because there's squares in the Pythagorean theorem, so I got a square root. Some triangles with certain side lengths have nothing but whole number sides, which is neat. It's not very common. Could somebody tell me, in relation to B, what's the y side?
7.
Yes. You just do that. And what I normally do is I'll tell students, okay, do this, and then you know that's y, you know that's x. Then you can just make all your shit. Yes? What's sine B then? Of course, this is h. 7 over 25, blah, 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 blah. Yes? Do you guys see what I'm saying? SOHCAHTOA, you wouldn't have to rotate it. You would just say, so sine is opposite over hypotenuse. But how much time did you save? Did you save much time? I need you to be with me on this. SOHCAHTOA supposedly makes things quicker and easier. It doesn't. How much time did we save? I just didn't have to rotate the triangle, so we saved about 0.7 milliseconds. Is it pretty cool with sine B is 7 over 25? Does anyone not see that? Let me know. What about what's cosine of B?
25 over 7.
No,
Oh, sorry.
not cosecant, cosine. Yes, 24 over 25. Good. Because that's the x side in relation to the b. Yes? Okay, I like it. Notice something. What is sine of a? Now what's the y side? If I'm talking about a. Yeah, 24. So sine of A is 24 over 25. What's sine of, you can do it, Jeff. What is cosine of A?
What?
What's cosine of A?
Oh, yeah.
Is A in the base? Yes, so what's the x side? 7. Hypotenuse? 25. Does anyone notice what happened?
They flip.
Sine of B is the same thing as cosine A, yes? Which really only makes sense. It's because of the symmetry in the triangle. If I say sine B, I want that to be in the base. If I say sine A, I want that to be in the base. So of course the two kind of flip. Okay, let me stop for a minute. So trig functions. I told you yesterday, we're going to do a ton. There's so much stuff you could do with trig. An insane amount. And we're going to get so deep down the rabbit hole, it's going to be easy to forget. But trig functions always come from where? Ratios of sides of right triangles. That's where they come from. That's all they do. Directly. Okay. I'm working towards you. Oh, good. Yeah. What if I told you I have a right triangle where tangent theta is 4 over 7? Oh, geez, Jeff, you almost made it the same problem. It'll be all right. Let me change this. This is too close to something I want to do later. I'll say secant theta is 11 over 3. We have a right triangle where secant theta is 11 over 3. Can you just draw the triangle? Doesn't have to be to scale, but I'll warn you the x side should be kind of big. Actually, maybe not. It should be that way around, but it's fine. Here's my theta. Now, secant theta. If you don't remember, secant theta is 1 over what? What's secant theta the reciprocal of? Okay, that's what secant theta is, but it's reciprocal of cosine, yes?
Oh,
So secant theta is h over x. So can somebody tell me how long is the hypotenuse? 11. And how long, what does 3 tell me?
yes.
Good. So if I tell you, hey, tangent theta is 5 over 6, you can draw the triangle. If I say cosine theta is 1 over 8, you can draw the triangle. You guys with me? Then I can ask you any damn question I want to. Like I could say, okay, great, what's tangent theta? Do I have all the information I need to figure out tangent theta? What am I missing? Say again? I'm missing the y side. And how do I get the y side?
I agree.
Old Greek tude. So that would be, how do I set up Old Greek tude here? You give this side a name. And how do I set up Old Greek tude?
A squared,
A squared plus
3 squared,
3 squared equals
11 squared.
11 squared. Good. So a squared is 112. A is the square root of 112. That actually you can do to a certain point. This would be, what is that, 4 times 28, I think? Which is actually 16 times 7. Neat. All right, let me slow down. I'm sorry. You guys know we have done this before, where you have to simplify radicals, yes? This is going to be a huge part of trig. You need, when you get something, you have to stop and say, can I break this down? And I realized 4 goes into 112. Did I tell you guys how to tell if 4 goes into a number? Any number in the entire universe. How can you tell if 4 goes into it quickly? What's the last 2 digits in 112? 12. Does 4 go into that?
Yes.
Therefore, 4 goes into 112. If 4 goes into the last 2 digits, it goes into the whole number. Did anyone know that before now?
Kind of.
3 1.
3 is if all the...
All the things sum to a variable of 3 gets divided by 2.
Yeah, if all the digits add to a multiple of 3,
Yeah.
3 goes in. 9 is the same rule because 9 is a multiple of 3. 4's rule is if the last 2 digits are divisible before the whole thing. Just go with me for a second. I know I'm talking about something different than trig right now, but this is huge. Why does that work? Does 4 go into 100?
Yeah.
Yeah, 4 quarters is 100 cents, yes. So 4 goes into 100. Therefore, 4 goes into 100 and anything that's a multiple of 4. Does 4 go into 112? Yes, because it goes into 100 and it goes into 12, yes? Does 4 go into 300? Yes, because 4 goes into 100. So of course it goes into 300. Therefore, if you think about what I just said, all I need are the last 2 digits to work, because it's going to work no matter what else. So if I have the number 38971439944, 4 goes into that number because 4 goes into 44. That's neat. Love it, guys. Even if you don't find it neat, it is. Yes.
How did we get from 112 to 4.28?
No, 4 times 28. Sorry.
Oh, 4 times 20. That makes so much more sense.
Hell yeah. And then I realized that's 16 times 7, yes? So that would be 4 square root of 7. So I can reduce the square root of 112, I can reduce it to 4 rad 7. You guys with me? You have to do that. It is the same thing as if you gave me the answer was 16 over 12. It might not be wrong, it's just you didn't reduce it, yes? So I look at the square root of 112 and I say, I could reduce that. Let me stop for a minute. Can we figure out what the tangent of theta is now? What's the tangent of theta?
4 square root of 7.
Yeah, 4 square root of 7. Over? 3. Yeah. So if I give you a trig value, you can draw a representative triangle, and you can answer any other trig question off of that. Yes? Very useful. Now, I did show you the tree thing, so I always want to go back to that. That's our one concrete, real-life example that I hope some of you guys realize is incredibly useful. Oh, now tall it towers. I don't want to climb the damn thing. I could actually use trig without having to climb the damn thing. That's incredibly useful. We could use trig to figure out how wide a lake is without having to cross the damn lake. That's useful. Okay, maybe.
You use a lot of trigonometry in construction.
Oh, God, yeah. And like I said earlier, the survey thing, my little brother hated math. He's the guy who says, Jeff, everything's 50-50, either it's going to happen or it's not. I'm like, James, I'm glad you didn't become a doctor. But he said he got trig when he shadowed surveyors, right? Because he was really interested. He was in the Army Corps of Engineers. He does all this amazing freaking, I don't know shit about cars and so forth. He could take one apart and put it back together. I'm like, that's cool. But when he shadowed surveyors, he was like, oh my God, trigonometry makes so much sense now. Because they're just measuring angles when they're setting their tripods. They're measuring angle differences, and then they can figure out how much the ground has either gone down or went up. You guys kind of with me? When you build somewhere, the ground can continue to settle, and if it gets to a certain point, you get a little worried about foundations cracking. So they have to come out and make sure that's not going to happen. So it's like in your face, holy shit, this is important, and oh my God, without trig, we couldn't do it. How you guys feeling so far? You guys all right? Have I imparted on you how important this is? Okay. Let me see. Am I ready to give you this? Yes, I am. So let me give you this so I can shut up for a little bit. And also, I think a few more people came, so let me double check. Does anyone need this handout from yesterday? Part 2 of the homework? Yes? Okay. Oh. Oh.
Are these both theta or is this something else? That,
Hold on, sorry. Make sure it didn't. Okay,
is that theta?
that's theta, yeah.
Okay.
Yeah, alright, it's kind of like, does everyone write their 4s the way I write my 4s?
No.
Okay, so theta, I do like this. Computer programs, that's the main theta that they use for the equation font.
Mm-hmm.
You with me? But theta to me is always going to be this. Anyway, I'll stop there. It's kind of like different accents. Tomato, tomato.
I heard that the rest of the U.S. the way they see California accents is that we don't enunciate our T's. Like we say water.
That always reminds me of the Southport Planet area. But yeah, like it's like butter. That sounds more British. What's the word I was thinking about? Oh, button. Button, if you think about it, there's no T in there. It's not button.
Button.
It's button. Yeah. Just to make sure everybody's on the right track, what's the very first thing you have to do for both triangles?
Flip them to the right spot.
Oh, you good. I like it. So, like the second one, you have to rotate it. But what's missing? One of the sides. So you just be sure you set up the Pythagorean theorem correctly. The most important side is the what? Hypotenuse, because that's C. It's got to be by itself. And I always give students that put those in the wrong places, and they end up with these impossible triangles, which is neat. Okay. Oh, sorry, yeah. What's happening? No. What is something divided by itself?
Oh, you're good.
Yeah, you're done there.
Oh, I was done. I just never thought it.
Yep. You used specific numbers though, so you proved it for one triangle. I want it to always be true. So what is x squared plus y squared? In this right triangle, you got x here, y there, h there. So what's x squared plus y squared? No. That's for the specific numbers you chose. So you're using. You got r. You're using this triangle, yes. What is x squared plus y squared? Don't overthink. No. Don't overthink. Yeah. So what can you replace x squared plus y squared with? If you put those together, it's x squared plus y squared over r squared. And then you know what x squared plus y squared is. Well, it's r squared, and that reduces, yeah. X squared plus y squared is r squared. Yeah. Alright, let's take a look here. Let me catch up to you guys. And you know, just to remind you, you've got to have Good old Pythagorean theorem, always ready to go. The most important side is the hypotenuse. It's got to be the side that's by itself. Why does it make sense? Because it's the biggest side. It should be composed of the other two sides added. I can't have smaller side equals bigger side squared plus smaller. No, I can't. That doesn't work. Right? And I showed you not really a proof, but kind of like a visualization. And I showed a few people this again. But if I draw little squares off the sides, and there's a really cool, I gotta look this up, there's a really cool video where somebody constructed something and these two are full of water. That's how I say water, by the way. And when he rotates it, they both flow and completely fill this one. Do you guys understand what I'm saying? There's water here and here, and then when he rotates it, all the water drains out and completely fills this. And that shows that this area plus that area equals this area, which is all Pythagorean theorem says. It says a squared plus b squared equals c squared. So the most important side is c. Whatever the hypotenuse is, it's got to be by itself. So on this one, I'm going to call this c because it is the hypotenuse. And how do I set up Pythagorean theorem?
5 squared plus 4 squared equals c squared.
Good. So then I get 25 plus 16. So c is the square root of 41, which a lot of you guys got. Don't make that a decimal because any decimal you write is going to be wrong. Because the only way to be right is to go forever, and I don't want to do that. So just leave it as square root of 41. Can I reduce square root of 41? No. 41 has no, I think it's prime. It has no square factors, so I can't reduce it. Yes? And now, I desperately, you do have to memorize some shit. You do. You really do. But the stuff you're memorizing is just how to set up ratios. All trig functions fundamentally are ratios of sides of a right triangle. I have a completely defined right triangle, even though I forgot to write one. Therefore, I can figure out what is sine of A going to be. My A is in my base, so that truly is the y side. So what's sine of A? Now, if you wrote this, you're fine, but I want to remind you, or maybe tell you for the first time, I can't remember. There's one little thing wrong with the way this is written. Square roots kind of suck in general, but this sucks especially because not only is there a square root, but I'm also dividing by it. So there's something we do, it's called rationalizing the denominator. Really silly question for you. Why can I take the square root of 9, but I cannot take the square root of 41? Let me ask you a better question. Why can I take the square root of 9, but I can't take the square root of 3 and write it as a nice number?
Because 3 is prime.
Because it's rational.
No. Can I do the square root of 15?
No.
That's not prime. So, it's because how many 3's are in 9? And what is the square root looking to do? Cut it in half. So I need to have 2 in there for the square root to be able to be done. So why can't I not do the square root of 41? Because 41, there's only one 41, and I can't break 41 down. So how do I make it so I can do it? What does it need? It's only got one 41 in it. What does it need?
Another 41.
Another 41. Aw, we're going to complete the little dude. Yes? He's waiting. Coming on. So we're going to give him, if I multiply the bottom by another square root of 41, I better also do what?
Multiply the top of the same.
Multiply the top. So then this is 5 square root of 41 over 41. And really quick, is everybody cool with that? Square root of 41 times square root of 41, this is square root of 41 squared is 41. So what's the square root of 11 times the square root of 11? 11. What's the square root of 38.2 times the square root of 38.2? 38.2. Half of 41 times the other half of 41 makes a whole 41. Now, some of you guys might think that looks worse. I think it looks better because at least our radical isn't dividing now. So with that in mind, what's cosine of A?
4 over square root of 41.
Yeah, 4 over square root of 41. Can you guys see what this is going to become now?
4 square root of 41 over 41.
Total. Kick ass. And then, of course, tangent's going to be nice. Tangent we knew from the beginning.
5 over 4.
Yeah, 5 over 4. Because tangent, I had all the sides it needed. So what's cotangent?
4 over 5.
Now, here's the trick. I'm kind of happy you guys did not, most of you guys that I looked at, didn't rationalize your sine and cosine. Because then secant and cosecant were so much easier. And I need you to realize they remain easy. I'm not going to make cosecant, I'm not using this shit. This is equal to this, so I'm going to use this. So how do I make cosecant?
Flip 5 over square root of 41. I find the reciprocal.
Yeah, so it'll be square root of 41 over 5, yes? And that's cool, yes, because the radical's on top. That's good. What's secant? Square root of 41 over 4. Okay. I really set myself up here.
How would you simplify it if you were to find the cosecant with the end result of the sine? So like
All
I'm trying
right,
to
if you
think
want
of
to
it
see
in
it,
my
so
head.
let's see. 5, real quick, 5 rad 41 over 41. That's sine, yes?
Yeah.
All right, just because. If I got cosecant to be 41 over 5 square root of 41, I've got to multiply by rad 41 for the same reason as before, yes? This becomes 41 rad 41 over 5 times 41. Is that cool?
Yeah.
Die, and then we end up with the same answer we got before.
Okay.
So it
That's
it
all
has to
extra
work.
steps.
It has to work. Because that's how we find it. It shouldn't matter which thing you flip. But I'm going to pick the easier one. Since it's got to work both ways, I'm going to pick the easier one. Is everybody kind of with me? So if you rationalize something, you have to. Rationalization is just part of the process. If you don't do it, you're going to lose some points. But if you rationalize something, don't use that rationalized version. Use the original. Because then you're sort of one step and you're done. You can see that. So that's why I was happy some of you guys did not rationalize it, because it made the secant and cosecant easy. You just could look at it and go, whip. You can still do it. Okay. Maybe. By the way, I can't help but say something. When I stop and I give you stuff to work on, please do God call me over if you're stuck on something. You're here. You're here. Look at everybody who's not here. They don't have access to me helping. And I'm not saying I'm amazing. I'm just the guy in the room that knows math really well. Yes? So if I give you stuff to work on, call me over if you need some help. That's the ultimate best time to do it. Yes? I'm sorry. It's just, it kills me. There's so many TCs, it kills me. And then you guys are here, but you're not using me. Right? Use me. Okay. What about this guy? What did you guys get? It's got one thing going for it better than this guy. Because what did you guys get for the last side? And just to do it real quick, this side I could call it B. That's definitely C, yes? There's no other option. So this would be like 5 squared plus B squared. Don't look up there, Jeff. Equals 13 squared. So I get 25 plus B squared equals 169. B squared is 144. We all should know B is 12. Good. Right? So it's got that going for it. But what's it got against it? What's kind of something I have to be careful about? The angle is not in the base. So if I just rotate it, what's my y side?
5.
5 is my y side. And B, which is 12, is my x side. So now when I construct all my stuff, now again, My SOHCAHTOA users, you can sit there and go, look at this jackass. I don't have to do that. Well, great. That's the one thing SOHCAHTOA does better. The one thing. So enjoy that. Yes.
So when you're flipping it, the right angle has to be,
In the base. Oh, sorry.
Yeah, like it should be kind of facing like the Y direction.
Should be in the base. Yeah.
Okay, okay.
So the right angle's in the base, and then whatever other angle's down there, that now sets up what my Y side is and my X side. Does everybody see that?
Either way you flip it, the right triangle's gonna be in the base. Or
Well,
the
if
right
I
angle's
put
gonna be the base.
that, if I put this angle in the base like this, now it doesn't even look like a right triangle anymore. Do you see what I mean? So yeah, I want to be a little careful. I think that's what you're asking.
Yes.
You always want the right triangle on the base, and then you want your angle you're interested in the base. Then this is the Y
Oh,
side.
okay, there you go.
This is the X side. Yeah. You guys with me? No? You hate this shit? I suck? Okay. So what's sine of A?
5/13.
Yeah, 5 over 13. The Y side out of the hypotenuse, cosine A, 12/13, tangent A,
5/12.
5 over 12, and then all these guys are quick and nice and easy because you just look at these guys and flip, flip, flip. Become a 3. Okay. So right now, I don't blame you if this feels like just an exercise in just writing numbers and flipping them, so you're like, ooh, this is amazing, Jack. But I already showed you, I keep going back to the tree because it's the one concrete example we did, but it's actually really powerful. That one example we did of the tree just illustrates the immediate stuff you could do with trig. It's insane. So this is reminding you that trig functions fundamentally are really simple. They're just ratios of sides of right triangles. The amount of stuff you can do with it is insane. And we're going to slowly build that up. But you can always come back to this. It's always based off of ratios of sides of right triangles. We did a problem just like this earlier. So what did you guys do first?
Use the pattern.
Well, I don't have a triangle yet. I haven't drawn it yet, so how do I draw this triangle? Well, I draw a right triangle. Which side is 2? It's not to scale, by the way.
What?
Yeah, the Y side's 2, and the X side is 7. Now, I want to say something, I don't want this to be confusing, but just in case. I could have made, I need you to understand this. I could have made this 4 and this 14. Tangent would still be 2 over 7 because that would still reduce, yes? So when I say I'm going to draw a representative triangle, it's kind of like the lowest terms triangle. I'm going to reduce ahead of time so I don't have to reduce at the end. I need you to understand what I'm saying. If I made a triangle, my triangle was this. What is tangent of theta? And what's 4 over 14?
2 over 7.
There. So there's how many triangles for which this is true? How many triangles have this true? Infinite triangles have that true. So what am I going to create? I'm going to create what I call the lowest terms triangle, right? Just the immediate triangle. Okay, I love it, guys. That's the idea we talked about yesterday when we doubled the size of the triangle, but the angles remain the same. So of course the trig functions remain the same. They all reduce to do the same thing. So what do I need to be able to answer the question? Do I have what I need to answer the question? The find cosine theta. What am I missing? Hypotenuse. Who am I going to get help from? Someday somebody's going to say old Greek dude. So we're going to use old Greek dude to figure out the hypotenuse. And how do I do that?
2 squared plus 7 squared.
So we'll get 4 plus 49. I get h is the square root of 53. Is that cool?
Yes.
And then what's cosine?
Square root of 53 over 7.
Careful, that would be secant.
7 squared.
7 over the square root of 53, which we then have to do what?
radicalize or rationalize.
We're making more math terrorists.
What would radicalize mean in math? Would that just mean adding unnecessary irrational numbers?
I mean, you could say like the step we did
Like
when we
taking
solved,
the last
when we
step and
solved, when we
reversing
solved
it?
for h. You could say we radicalized the form of the equation, but nobody would say that.
Okay.
If you said that to a math person,
That doesn't
they might
exist in math.
Just, they might just walk away from it. I don't know what would happen. Or you know, if it was me, I'd be like, oh, that's a neat way to say it. Now, proof questions always freak people out. But if I just draw the triangle that everything here is based off of, what is cosine from the triangle? What's cosine?
X over R,
X over r. And what's sine?
Y over R.
So then I get x squared plus y squared. Since the bottoms are the same, I can just add those. But from the triangle, what is x squared plus y squared? What is x squared plus y squared? What does Pythagorean theorem say? X squared plus y squared equals?
R squared.
Yes, so wherever I see this, what can I replace it with?
R squared.
This, because it's equal to each other, yes? So how do I rewrite this?
R squared over R squared.
Which is
Or
1. Yeah.
or x plus y, x squared plus y squared over x squared plus y squared.
Good, you could do the replacement either way. I love it. They are both the same, so the ratio is 1, no matter which way you go.
What if it equals 0? Then you don't have, never mind, you don't have a triangle.
Then we're in some different universe. Yeah.
So you can look, did you radicalize, or what is that? Is it R squared? The bottom.
Sorry, let me write that better. What is x squared plus y squared?
R squared.
So I can replace this with r squared, and then what's r squared divided by r squared?
1.
So we proved it. That is true for what angles? You can do it. You can do it. You can do it. Did I have to draw my triangle this way? All I need is a right triangle. Yes, that's all I need. So what angles does it work for? Every angle. That is always true. It is always true that cosine squared theta plus sine squared theta equals 1. That is simply true. Let's try it. Look at this problem up here. Look at this problem here. Shut up, Jeff. Look here. Let's try it. Sine squared plus cosine squared. Is everybody with me? What is that? What's this? 5 squared is 25. 13 squared is 12 squared. What's 25 plus 144?
169.
Now that is not a proof. You cannot prove a damn thing using a specific example. That is an application. Not even an application, just a verification. We're just verifying that for this specific triangle, that general thing holds. So you have a whole new way. If I tell you what sine A is, and I say what's cosine, you could actually just plug it into that sine squared plus cosine squared equal. You can solve it that way. It's a whole new way to do it. Now, listen, just to point this out. I need you to understand. If you know Pythagorean theorem, this kind of problem has to be easy. It has to be. Let it be easy. Let it be easy. The hardest part, I think, is going to be memorizing shit. Always. Yes? But all you have to know are the first 3. And the others, you're just flipping those over. Yes? So let this be nice. Even if there's radical shit. It's just one little extra step at the end. You're just making ratios. Okay. What was I about to do? I forgot. There we go. So, last thing for today. I do want to introduce something I want to talk about angles. So we're sort of getting back into 7.1. Everything we've been talking about is basically from 7.2. 7.1 talks about angles, but I like to introduce trigonometry as for what it is. 7.1 to me is sort of like an extra little, oh yeah, degrees kind of are not good. Degrees are not good. Listen, why are there 360 degrees in a circle?
As we say so.
Totally. We could have said it was 100 degrees. If we were like going more like a metric system, yes? We could have said there were 2 degrees in a circle.
There's I degrees.
Yeah, we could have said there's I degrees if we were exceptionally high. But one reason we like 360 is you can factor it a lot of ways. We also kind of stole it from the Babylonians. We stole our time system, seconds and minutes, 60 seconds in a minute, 60 minutes in an hour. We stole it from the Babylonians because they had a base 60 number system. We have a base 10. You guys kind of with me? So America, we're really good about stealing language, and we steal numbers, and we steal numerical values. And then we kind of say, look at us, we're right. This sucks, though. This totally sucks since it's completely made up. It's not real. It doesn't measure anything real. It's just made up shit. Because I want an angle to be based on something physical. We need angles to be based on something physical. So, somebody help me out. Do you guys remember, for a circle, looks like a very contented circle. For a circle of radius r, does anyone remember what the circumference is?
The entire square?
That's area, because your units would be squared.
Pi r?
Closer. So, do you guys know what pi is?
3.14.
Well, you could never finish that, so no. If I take any circle in the entire universe, any circle in the entire frickin' universe, and I take its circumference and divide it by its diameter, you get the same number. So civilizations realize this. Because, before the internet and everything, they were like, what do we do? Let's draw circles. So they said, holy shit, no matter how small or how big the circle is, we keep getting the same damn number. The Egyptians had an estimate. They said 22 divided by 7. If you do 22 divided by 7 in your calculator, it's pretty decently close for not having any freaking technology. Yes? You guys, yeah, you don't get it. Other civilizations had other approximations. I need you guys with me. In fact, if I took a piece of yarn, and I've done this before with my math for elementary teachers class, take a piece of yarn and go around the base of a trash can or something, and then you lay it out. You can actually measure the diameter of the trash can, and if you lay the yarn out, you can measure the length of it. That's the circumference of the circle, yes? And then you divide those numbers and you get roughly pi. You don't get exactly pi because you're just human and yarn is kind of stretchy, so you're going to get kind of, you guys kind of with me? Okay. And I have some people using like the base of a mug, the base of the trash can, like different size circles. So this is where pi comes from. We just said, oh, that's always, this divided by this is always the same number. That would freak us out. It did. We decided to give it a Greek letter because Greek letters are like, ooh, look at that. So then the formula for circumference, I just multiply by d. Now, what's the diameter in terms of radius?
Circumference divided by pi?
No. What's the diameter? What's the diameter in terms of radius?
Oh, it's double the radius?
Yes. So that is the formula that you should normally kind of know for circumference of a circle. 2 pi r. Man. All right. No. There's going to be too much to get into. It's so flippin' cool, though. Real quick, if I take this radius, if I physically pick that radius up, put it down, yes? There it is. And then I come over here and I go, and I bend it so that it will fit on the circle. Yes? So I bend this, and then I put it back on the circle. Is everybody with me? So this length, even though it's curvy, it's still R. If I walk in a curve, I can still walk a linear amount of feet. Yes? Do you all agree I just went through an angle? If I do that, that angle is 1 radian. Because how many radii did it take to get me to go through that angle? 1! Do you understand how dumb that is? And is that physical? Is it based on a physical measurement? Yes. And if my circle gets bigger, my radius gets bigger, I therefore end up at the same exact place. So the angle is still 1 radian. Be with me. So where would 2 radii, what would the angle of 2 radians look like? Well, it would just be 1 more radius's length, yes? And that would be 2 radians. You guys semi with me? Now, obviously, there's more to it, but I at least wanted to get there.
How many radians are there in a circle?
You tell me. Real quick. If the radius was 3, and I walked 6, what's the angle? 2 radians, yes?
Yeah.
Okay, so what's the circumference of a circle? 2 pi r. So 2 pi radiuses. So how many radians in a circle? 2 pi. There's 2 pi radians in a circle because it takes 2 pi radiuses to get around it. Because the circumference is literally 2 pi radiuses. So that's 2 pi radians in the circle. I'm really sorry that was quick at the end. We're obviously going to unpack this more tomorrow. I'll see you guys then. Yes?
So I think 1 pi is 180 degrees.
Yes, totally. So if all the way around is 2 pi, 180 is 1. And that'll be what we use to convert between radians and degrees. Yeah, good.